This is the fifth and the last part of this lecture. In this part, we shall take up three topics to discuss, namely renewable energy methods, current status of renewable energy, and future directions. As of the topics we discussed in the previous parts of this lecture, we have come to an idea that there cannot be a possibility of looking back towards continuing the old methods of harvesting energy from fossil fuels and risking the life further to a new height of damages and dangers beyond control. We should now focus to develop the workable and sustainable energy mechanisms. The topics we shall discuss in the next few lectures are solar energy, wind energy, ocean energy, geothermal energy, and bioenergy. The first in the list is solar energy, which is the radiant light and heat received from the sun that can be harvested in the form of utilizable energy, that is, electricity, heat, and so on. Areas at or closer to the equator have a higher amount of solar radiation. As we can see in this picture, the equator region receives the straight rays. The regions between the Tropic of Cancer and the Tropic of Capricorn in the form of a belt region receives solar radiation the maximum compared to the rest of the regions on the globe. The theoretical areas of the small black dots is sufficient to supply the world's total energy needs of 18 terawatts with solar energy harvest. The practical challenges are the availability of the land and equipment. The solar panels could be set up on the lands which is either unused or not to be used for any business purposes. The different solar energy harvesting methods are solar heating, photovoltaics, solar thermal energy, solar architecture, molten salt power plants, and artificial photosynthesis. Solar heating method employs rooftop panels for absorbing solar energy for water heating. Also, the solar heating can be used for heating air in the houses during the cold winters. Solar air heating system captures the heat by an absorbing medium and propels it inside the house to keep it warm. Here is a picture on the left side showing solar water heating system deployed on a rooftop. On the right side is a solar air heating system which captures heat by an absorbing medium and use it for heating air. Solar thermal energy methods harvest solar energy to produce higher temperatures than solar heating. The heat produced by these methods is enough for running kitchen. It can also be designed for producing enough heat to run an industry or even produce electricity. Here in the picture, we can see solar bowl installed above a solar kitchen which concentrates the sunlight on a movable receiver to produce steam for cooking. Another picture is of solar furnace where solar panel arranged with mirrors concentrate the solar radiation to produce temperature up to 3500 degrees Celsius, enough decent to run an industry. Photovoltaic cells are made of silicon wafer and work on the principle of photoelectric effect. This device generates electricity directly from the sunlight. The photovoltaic cells can be arranged to construct solar panels to cover the rooftops to build solar settlement and sustainable housing communities. Solar architectures are under constant research so as to bring the best yet cheapest material to build energy efficient homes. The photovoltaic tiles on the roofs are one such example, which are smaller in size and sit perfectly onto the tiles of the roofs. This not only saves material but also saves lots of space over the rooftop. Alternately, photothermic modules on the rooftops produce heat energy for the houses and are very effective in constructing greenhouses for vegetation. In the molten salt solar power plant, molten salt is used as a heat transfer fluid (HTF) and thermal energy storage (TES). The salt used in these systems is low melting ternary mixture of molten salts with a melting point of 131 degrees Celsius that can be used as both a heat transfer fluid and thermal energy storage of concentrated solar power plants. These types of power plants have an advantage because the molten salt is liquid at atmospheric pressure and provides a low-cost, inexpensive medium, which is also non-toxic and non-inflammable and sufficient in storing energy when sun is not shining, that is during the night times. When the energy is required, the salt is pumped through a steam generator that boils water, spins a turbine, and generates electricity. Here in the second picture, the molten salt solar power plant is constructed with 10,000 mirror heliostats spread over 1,600 acres of land, which collectively focus the sunlight on a 640-foot tall central tower fitted with molten salt chamber. The salt is heated by the focused sunlight up to 1000 degrees Fahrenheit, which is then converted into either electricity as and when required or stored as heat energy. Another advantage of such power plants is its efficiency, as it can store heat for months at a time, so that even if during the cloudy days the availability of electricity is not interrupted. Furthermore, it has zero emission, minimal use of water, and no hazardous waste remaining to be disposed of. Artificial photosynthesis is a chemical process of biomimicking the natural process of photosynthesis. Natural photosynthesis converts sunlight, water, and carbon dioxide into carbohydrate and oxygen, and that is how the solar energy is stored in the form of newly formed chemical bonds. In the artificial photosynthesis, the efforts are focused to store solar energy in the form of chemical bonds of solar fuels, such as hydrogen or hydrogen peroxide, while photocatalytic water splitting produces hydrogen and oxygen. The photons resulting from water splitting can be used for hydrogen production, and this method of sustainable hydrogen production is an achievement in terms of achieving a clean fuel. These catalysts must be able to react quickly and efficiently to absorb a large percentage of the incident solar photons. Wind energy is a form of solar energy, and the kinetic energy of the wind can be made to move the turbines of a generator to produce electricity. Wind power is a sustainable and renewable energy and produces clean energy without affecting the environment significantly. As of now, 83 countries are using wind power to supply their grids. Wind turns the propeller-like blades of a turbine around a rotor, and thus the kinetic energy of the wind is converted into mechanical energy. The moving rotor can be utilized in several ways, such as grinding grains, pumping water for irrigation, and producing electricity. For producing electricity, the moving rotor is connected with a generator which creates electricity. The three most popular kinds of wind power generation are inland wind farm, onshore and offshore wind farms. Inland wind energy farms, which is a group of wind turbines several hundred in number, distributed over an extended area. Onshore wind farm is installed at the ocean shorelines, enabling the inland areas to remain available for agricultural purposes. Here in the pictures, onshore wind farms are shown. Onshore wind farms provide cheaper mode of energy which can possibly benefit to the two-thirds population of the globe. Offshore wind farms are constructed in large water bodies off the shoreline to generate electricity, thus sparing both inland areas and the shoreline areas. Although offshore installations can utilize the powerful winds more frequently but involve huger cost compared to the onshore or inland wind farms. Offshore wind energy farms in shallow waters have been extensively researched on and considered as a proven technology. On the other hand, transitional water and deep water wind farms in the depth ranging from 30 to 60 meters and beyond 60 meters are still under demonstration. Ocean energy is also known as marine power or marine energy and hydrokinetic energy, which is associated with the ocean waves, tides, salinity, and ocean temperature difference. The kinetic energy in the moving ocean waters can be converted into mechanical energy and finally into electrical energy to power homes and industries. Marine energy is harvested by means of different designs of turbines installed at different locations inside the ocean waters. There are mainly 5 forms of marine energy that is being worked out and researched on, namely tidal energy with a potential power generation of more than 300 terawatt hours per year. Other forms are marine current power with more than 800 terawatt hour per year, osmotic power or salinity gradient with 2000 terawatt hours per year, ocean thermal energy or the thermal energy gradient with 10,000 terawatt hour per year, and wave energy with 8,000 to 80,000 terawatt hours per year. The picture here presents the main 5 forms of marine energy installations. The wave energy is harvested in open coastal areas where significant waves are in constant motion. The tidal turbines are installed in the coastal and estuarine areas. Ocean current turbines are installed in the areas which receive strong marine currents, and the ocean thermal energy converters are installed in deep tropical waters. It is estimated that there is possible to develop 20,000 to 80,000 terawatt hours per year of electricity that can be generated from ocean temperature gradient, salt content, movement of tides, current waves, and swells all put together. Indonesia, which is an archipelagic country, has the 3/4 of the area being its shoreline and in direct contact with the ocean, has 49 gigawatts of recognized potential energy and has 727 gigawatts of theoretical potential ocean energy. We shall study in detail in our upcoming lectures. Geothermal energy is the harvest of thermal energy which is stored inside the earth. The thermal energy inside the earth is generated from the radioactive decay and continuous release of heat since the earth's formation, and the temperature inside is over 4000 degrees Celsius. Such a high temperature and pressure inside the earth is enough to melt the rocks, and the solid mantle becomes plastic and behave like fluid. This results in a portion of the mantle to convect upward and heat the underground waters as well as the water on the ground, where the crust is thin. This heat is sometimes 370 degrees Celsius and can be utilized for generating electricity. Geothermal power is cost-effective, reliable, sustainable, and clean energy. We shall see this in detail in our upcoming lectures. Bioenergy comprises traditional biomass and heat energy derived from it. Besides this, ethanol, biodiesel, and biopower generation are the other forms. Biomass energy has been harvested by the human beings since the beginning of the civilization. Biomass is plant or animal material such as crop residues, wood or forest residues, food waste, animal or human waste, or the sewage. Although the energy can be harvested by burning of these biomass, which produces carbon dioxide, but it is still considered as renewable energy because the process of photosynthesis cycles it back to the new crops. We shall see this topic in detail in our upcoming lectures. Biomass is organic material which has directly or indirectly stored energy from the sun in the form of chemical energy. Here in the picture below is the biomass generated from agricultural harvest residue, which is either utilized as cattle feed or bioenergy. The second picture is of a sugarcane ethanol power plant producing electricity from bagasse residue obtained from sugarcane harvest leftover. Besides biomass, the other form of bioenergy are bioheat fuel, ethanol, ethanol and gas, biodiesel, methane and biogas. Bioheat is a blend of ultra-low sulfur home heating fuel with conventional oil or biodiesel obtained from domestically grown crops such as soybean, sunflower, linseed, and sesame. The crop oil is 100% renewable and convenient to grow and process. Biodiesel can also be obtained from animal fat, recycled grease, algae, etc. Bioheat is a more eco-friendly alternative to both traditional heating oil and natural gas heat at 12% of biodiesel and beyond in the blend. The blend can range between 2% to 20% of biodiesel. Biodiesel is produced with the help of a chemical process called transesterification. In this process, methanol is reacted with fat or vegetable oil to produce methyl esters and glycerin as a byproduct. The methyl ester is purified and utilized as biodiesel. Ethanol is obtained from biomass which include grain crops or crop residues such as sugarcane bagasse that contain high starch and sugar content. Other crops in this category are corn, sorghum, barley, sugar beets, etc. The crop residue is fermented, followed by distillation and dehydration of the liquid to remove water. The latter is important when ethanol is blended with gasoline and water may damage the engine of the vehicle. Ethanol is renewable as it is produced from biomass. Burning ethanol to produce energy is considered to be clean as the crops from which it is created absorbs carbon dioxide to grow. Methane is used as an energy source such as in a boiler to produce steam for electricity generation for household or in industrial processes. Methane is also used in fuel cells which are much like batteries and produce electricity. Methane is generated in different ways, namely natural anaerobic digestion process involving bacteria to decompose organic matter in the absence of oxygen. The decaying or organic matter also takes place in landfills or marshy lands and can be drilled out and transferred through pipes for cleaning and burning to produce energy. Another method is gasification of biomass at high temperature and an oxygen-starved environment to obtain a mixture of gases, namely hydrogen, carbon monoxide, and methane. This gas is utilized in fueling gas turbines to turn on an electric generator to produce electricity. Biopower or biomass power is the electricity generated from biomass. There are available many major types of biopower systems, namely direct fired, co-firing, gasification, and aerobic digestion, pyrolysis, small and modular. The direct fired system is the most widely applied biopower methods, and this employs direct burning of the feedstock to produce steam. The steam is captured by a turbine of a generator which rotates to produce electricity. The steam can also be utilized to harvest the heat energy. Generally, wood waste is used to produce both electricity and steam at paper mills. Co-firing is employed to reduce emissions, especially sulfur dioxide emissions. It involves bioenergy feedstocks as a supplementary energy resource in high-efficiency boilers to produce electricity. Pyrolysis is thermal decomposition of biomass at an elevated temperature and inert atmosphere or absence of oxygen to produce gaseous or liquid fuel. A small modular system generates electricity at a capacity of 5 megawatts or less for use at a small town level or at consumer level. The cogeneration station in Metz, France, uses waste wood biomass to produce biopower. The wood is collected from the surrounding forest. Cogeneration stations are also known as CHP, that is, combined heat and power. The picture below is the CHP station in Denmark, and it burns straw as fuel. Now we shall discuss about the current status of renewable energy. The total amount of electricity consumed worldwide kept on increasing, as we can see the trend in the year 2000. It is 12,116 terawatt hour. A terawatt is 1 trillion watt. In the year 2005, it increased to 15,105 terawatt hour, and it increased to 16,503 and 19,504 terawatt hour in the year 2008 and 2013 respectively. In the year 2018, the world electricity production reached to 26,700 terawatt hour. A major share comes from coal and gas, followed by hydropower, nuclear, and solar plus wind energy. As we have already seen previously that uses of fossil fuels have created huge amounts of carbon dioxide and greenhouse gases, which has caused global warming. To address this problem and to limit the global temperature to a hypothetically 2 degrees Celsius rise would require a decline of 75% of the carbon emission by the industries by 2050 if the world's population rises to 10 billion by this time. The renewable energy resources contributed 18.1% to the world's energy consumption and 26% to its electricity generation in 2017 and 2018 respectively. The energy consumption from renewable energy resources has 9% share coming from traditional biomass, 4.2% from non-biomass or heat energy, 3.8% from hydroelectricity, and approximately 2% electricity from wind, solar, biomass, geothermal, and ocean power. Here is a map represents solar resource available for power generation. It represents the average daily, yearly sum of global horizontal radiation, that is GHI. The places near or at equators receive most of the solar radiance. The installed global solar power capacity in megawatts has increased since the year 2000 from 1250 megawatts to 485,000 megawatts in the year 2018, with most of the progress acquired in the last 5 years due to the increased support from the improved technology and infrastructure. This world map provides an estimated summary of wind speed 100 meters above the ground surface level, and we can see the most of the regions where the wind power can be harvested are located at or near the coastal regions in far north and far south hemisphere. Yearly, the wind energy production grew 10% and reaching 4.8% of worldwide electric power usage. In the year 2019, 15% of the electricity consumed in Europe was supplied by wind power, and 4.8% of the worldwide electricity power usage came from the wind power. Denmark became the top among the countries to penetrate wind power at the maximum, with 43.4% of its total consumption of electricity coming from wind in 2017. As of now, 83 other countries are using wind power to supply their electrical grids. In the year 2000, 17,000 megawatt worth capacity of wind power installations were operating, which grew to over 200,000 wind turbines in operation, generating 432 gigawatts worldwide, and in the year 2018 it reached to 563 gigawatts. The global renewable energy capacity is projected to increase by 50% from the year 2018 to the year 2024. In the past few decades, the prices for solar and wind has gone all-time low. Although the installation costs are high in the beginning, but once operational, the cost of power supply is very less. This is unlike the fossil fuel run power supplies, which keep on mounting costs for energy. Solar and wind power is more executable for supply to a larger population on the earth compared to the geothermal, marine or ocean energy and the biomass. Solar and wind does provide clean and cheap energy. With extended installations of energy infrastructures and favorable conditions, it is possible to produce hundreds of gigawatts of electricity. The challenge is the wind is not blowing every day, or the sun is not shining on cloudy or rainy days, and demand for energy remains steady no matter how the weather is. Therefore, the need is to develop devices to store energy for such emergency. The main option right now is lithium ion batteries, and we see them in products like Tesla's home batteries and utility scale system like Power Pack. Although the prices of lithium ion batteries have gone a bit cheaper, but still too expensive for the most grid scale applications. To get a battery for an electrical grid, we require the reduction involved in the cost for production by 10 to 20 times. Right now, the capacity of lithium-ion batteries to store charge to supply energy is not more than 4 hours. Additionally, there is risk of fire, as it happened in many of the cases. Also, the ability of holding charge fades with time. As a solution, both chemical-based and non-chemical-based batteries are being researched on, involving every single possibility from any element present in the periodic table. One of the workable solutions are flow batteries. A typical flow battery consists of two tanks of liquids which are pumped past in an ion exchange membrane held between two porous electrodes. The two tanks contain anolyte and catholyte. Here we take an example of vanadium redox flow battery to understand the mechanism and working. It consists of two tanks storing vanadium anolyte and catholyte, and a pump is used to flow these electrolytes through the cell with two porous electrode chambers separated by an ion exchange membrane, forming the two half cells where the electrolytes are chemically oxidized and reduced to reversibly convert electrical energy to chemical energy. A PV installation or an external energy source is utilized to charge the flow battery, that is, storing the energy of solar cell module, and the electrical energy is converted to chemical energy during the charging process. The electrolytes are charged within the cell, are flown back to the tanks, which determines the storage of the charge. The cell chemistry involves redox reactions of vanadium. At the catholyte half cell, vanadium 4 is oxidized to vanadium 5. This yields an electron, which is driven to the external circuit, and the hydronium ion created simultaneously moves across the ion exchange membrane to enter the anolyte half cell. At the anolyte half cell, the electron from the external circuit enters and reduces the vanadium 3 to vanadium 2. The hydronium ion here balances the overall charge of the half cell. The two electrolytes leave the cell in the charged state of vanadium 2 and vanadium 5 respectively. During the discharge process, the chemical energy stored in the battery is now converted into electrical energy, feeding the external load. In the role reversal, vanadium 2 is converted into vanadium 3 and a hydronium ion crosses the membrane. Vanadium 5 is reduced back to vanadium 4, consuming an electron and the hydronium ion, and the electrolyte leaves the discharged cell in the form of vanadium 3 and vanadium 4. The process continues until the entire tank is exhausted or discharged. The flow batteries can be independently scaled for appropriate power and energy, and the power can be adjusted by increasing the cell size, additional number of cells, and expanding the tank volume to meet with the requirements. The main advantage of such flow batteries is negligible or no loss in the power capacity takes place due to the side reactions beside the main electrochemical reactions as observed in the conventional batteries, and the lifetime is longer than any other storage systems. Even the deepest discharge does not influence the battery health. The composition of the electrolytes, vanadium salts dissolved in dilute sulfuric acid, is considered to be safe in view of hazard potential as well as inexpensive mode to store the energy harvested from renewable resources efficiently. Although the battery technology is still to gain maturity and a commercial acceptability, we continue to research on to achieve better results. Currently, about 96% of the world's storage comes from pumped hydro technology. The system works on a simplified mechanism. When there is excess energy in the grid, it is utilized to pump water to the upfill, that is a reservoir, at a high elevation. And when there is energy demand, the water is released, which then flows down towards the bottom reservoir, passing through the turbine, generating electricity. But this requires a lot of land and disrupts the environment and functional in specific geographies only. Next in the list is energy vault, a gravity-based technique to store energy, and the company was founded in the year 2017. This idea offers much more scalable energy, low cost and no harm to the environment. Instead of moving water as we have seen in the previous case, Energy Vault uses cranes and wires to move 35-ton bricks up and down depending on the energy needs, and the process is automated with machine vision software. The system tower cranes utilizes the excess solar and wind power energy to drive motors and generators to lift the stack of bricks in a very specific sequence, and when the power is needed, the same system lowers the bricks and discharges the energy for supply. Although this technique is a promising breakthrough, but the size of operation is a difficult aspect to replace the chemical batteries. Next is the thermal storage systems, which is still an emerging technology in this space, and it has been demonstrated to hold energy for longer duration in comparison to the full chemical batteries, and that too with smaller footprints than the gravity-based systems. It is based on the principle that when there is excess energy in the grid, it is utilized to heat up the cheap carbon blocks, which are then insulated inside a container, and then the heat is stored. As and when needed, this heat is converted back into electricity using a heat engine, which is a typical steamer gas turbine. In the past, this technique had been very expensive to materialize commercially. This problem is technically being solved using a novel type of heat engine called Thermal Photovoltaic Heat Engine, TPV for short. It is based on the design of the typical solar cell, but instead of capturing sunlight and converting it into natural electricity, this solar cell captures the light radiated from the hot storage medium and converts that to electricity. The future of renewable energy is to design and develop an efficient energy storage system or device. It is estimated that when we get to roughly 20% of our peak demand available in storage, we will be able to run a renewable only system, and the future is not going to be a mirror of the past. This brings us to the end of the lecture 2. In the next lecture, we shall have some more interesting information to share and discuss.